Thanks. All right, so thanks to the organizer for the opportunity to speak here, and thanks to everybody for all the discussions and this great meeting. So I'll be talking about some work that appeared some time ago now with my student Hector, who's kind of there at the back, and some work to appear. Now, to appear can be a tricky statement, but I believe that now it's actually in a time frame of weeks rather than months. So I'm looking forward to it finally concluding. Those of you who've been to my talks before have been advertising these results for a while, so I apologize for being a bit repetitive. But since this is a student somehow meeting, I kind of try to simplify some of the things, and so again, I apologize for those who know everything already about what I'm going to say. But I'll just make some things a little bit more somehow basic than I would normally do. All right. So first of all, okay, there was a question. Okay, where is Pretoria? So just to point out for the international visitors that okay, it's close to Johannesburg up there. And it's the capital of South Africa, and it's a nice little city with lots of jacaranda trees from Argentina. So already there's a very strong connection between the story. So yeah, and when they bloom in October, of course, it's a very beautiful landscape. And the university also has quite a few jacarandas and also some old buildings, but that's not the building where we are based. So anyway, so let me get to the outline of what I want to talk about. The talk is roughly organized in 3 parts. First, I'll explain what is this Hopf and quasi-Hopf algebra that I'm talking about in the title. Then I'll go to the kind of first part of the title and discuss the exactly marginal deformations of n equals 4 and how they are related to these Hopf and quasi-Hopf algebras. And finally, I'll make some use of these ideas by defining something known as a Drinfeld twist and defining a star product, which will be quite instrumental in what I would eventually want to do with these theories. Okay, and please ask if anything is too technical or wrong or whatever. Okay, so let me start from the very basics, of course. So we all like Lie groups and Lie algebras, and they are the main way that we have to describe the notion of symmetry in physics. So I'm just writing here for the students, just a group element as the exponential of some algebra generators, which I call T. This is just very generic at this stage. And for an example that everybody here should know, in the theory of SU2, which describes spin in quantum mechanics, these specific generators are, well, you can choose a basis which has these 3 generators, and you all know that these are related to Pauli matrices in this particular way. Now, one interesting thing about SU2, and mostly algebras we care about, is that the product of these generators is non-commutative. So if you multiply Sx with Sy, that's not the same as Sy times Sx. And that, of course, leads to most of the interesting things that happen in physics in 4 dimensions, well, in 3 plus 1 dimension, but in general. Now, the point about these algebra elements, so the generators, is that naturally they act on representation spaces. Now, sometimes I'm going to kind of forget myself and call this a module, okay, which is a mathematical statement, but think of it as a representation space, and in quantum mechanics, it's just the Hilbert space of states on which you act with your generators. Right, so think of some states, and if you're working with the fundamental of SU2, then you would have, you can choose again a basis of 2 of these up and down, and act with these operators, and of course you cannot clearly diagonalize all of them at the same time, as you've learned in quantum mechanics, but for instance, if you choose the eigenstates of SZ, you can define your up and down states to have these different eigenvalues. Now, the question I'm going to ask is, how does this, well, the answer is given in the title, but how does this S, which would be the matrix, the operator which contains Sx, Sy, and Sz, the vector that you write there, how does it act on a product state? Okay? And that's something very common, very typical in quantum mechanics. You don't want to act on 1 electron, you want to act on 2 electrons, or L electrons, right, in a given spin chain, for instance. So how does that act? Well, the answer is it acts via, well, in this particular way, via this thing delta, which I'm going to call a coproduct. So, and as, again, it's something that everybody does very naturally, and we've all gotten used to this. When you want to act with S on a product, well, first S acts on this one, and then S acts on the second one. Right, so you act on the first and the second of your tensor product. So what we've just done is used a coproduct, which abstractly looks like this. So for any Lie algebra generator, you would write it like that, and then this acting on the product state gives us the usual rules of how spin acts. So the vector of spin can act on a product state, and you can combine these. You'll see some more formulas later. You can compose these if you have 3 states. This is only for 2 states, but it turns out that for a Lie algebra, if you have 3 states, then the natural thing would be x times 1 times 1 plus 1 times x times 1. So basically, the symmetric combination. Now, the interesting feature from my perspective about this, of course, this is somehow very well understood, is that this is co-commutative. Now, co means something that has to do with the tensor product structure. So it's not the usual, this is not a normal product. The product is when you multiply Sx times Sy or Sz times Sz in the same copy of your space, that you're acting on, so basically the same copy of the algebra. Here, when I say co, that has to do with the tensor product structure. And what you'll see is that if tau 1, 2 is the element which exchanges my 2 copies of my tensor product, then this is the same. So it's co-commutative. Right? So it's commutative under, if I act on it on states 1 and 2, or I act on states 1 and 2 and then I exchange, then I get the same thing. Now the Hopf algebra of the title is what happens when you allow this to be non-co-commutative. And just as a little bit of, I'm not going to go into the technical details, so you can ask me later if you want to see more of these.
For the example you just gave, could you go back to the slide? So, yeah. Could the most general Hopf algebra then be exactly above, but with different coefficients?
Different here.
Yeah, instead of 1 and 1.
Yes. For instance, and that's actually some typical scenarios are when we put a Q here in terms of the second product, and that leads to something like SU2Q. I mean, it's a bit more complicated. It's not exactly Q, but and the thing is, to make a consistent algebra, it's not enough to just multiply something here. You would have to, maybe for different generators, you need to have different co-products in order for everything to fit together. Because what will happen if you and you can test this, it's very simple. Just put a Q here. What you'll find is this is not going to be associative. Okay, if you do it, if you do it twice, like first 2 of them and then the third and then the other way around, you're going to mess up something there. Okay, which of course I will gladly mess up in a minute. So it's not something. There's nothing wrong with it. But for the usual quantum groups that you see, like SU2Q, I mean, you have to think a little bit more carefully about. Basically, you take your SL2 bases, x plus, x minus, and h, or something, and then the action is different on each of these 3. Okay, so it's not the same for IC. But it works out so that everything is nice and associated. Okay, so when I say associative, I mean co-associative. Okay, so what is an algebra? Just to remind you, it's a vector space, which means you have the usual relations that we like in vector spaces. You can add things in particular. Things have their opposites, so you can add them to 0 and all that. And together with a product, which takes you from 2 copies of the space to 1 copy. Okay? And one simple way of explaining it, and if these are kind of, if these give you the same element, this is kind of abstract. I'm not claiming that the element that you get here is exactly the same as the one you get here, but if it is, then you have something known as associativity of the algebra. Basically that if you first multiply these 2, that's what this means. You multiply the first 2, and then you do nothing. ID means you do nothing on the third one. So then you get 2 copies, then you multiply these 2, and you get an element. If you do it the other way around, and this element is the same, then you have associativity. But in general, when I write the statement, this doesn't have to be associativity. I'm just saying that you just get a single copy of the algebra. And there are more diagrams having to do with the identity elements and all that, which I'm not going to give. Now, what is a co-algebra? Well, it's an algebra where you have a co-product, and the co-product does exactly the opposite to you. It's what we had when we had this generator S, and you want to act on 2 copies, so you need to make S act on 2 copies of your representation space. So it needs to live in 2 copies of the algebra. And that's what delta does. Okay, so it takes you up here, and if you do this and you do that, and you get the same element, or in this triple product space, then you say it's co-associated. And there are definitely more diagrams that I'm not giving. And finally...
Sorry, may I ask you, so the difference between left and right is exactly applying or not the K12 first?
Yeah, so here, okay, so up to here you get the same thing, but now you see delta takes a single element and gives you these 2 elements, while ID does nothing. A stays A.
Oh, so these 2 arrows are the same?
Yeah, so up to here it's the same.
Oh, I see.
But here, this delta acts on this one, and it's a single element, you have to get 2 elements out. So it gives you 2 elements. Now here, delta acts on the second one, and it gives you these 2 elements. So the questions are, is this the same? And if it is, it's co-associated. All right, so now what is a Hopf algebra? Well, actually, first of all, what is a bi-algebra? It's a structure where both the downward going diagram and the upward going diagram work together in a compatible way. So you have a product and you have a co-product, and you have many other elements. You have a unit, a co-unit, and if you also have an antipode, which is an element that takes you from the algebra to the algebra, which satisfies this relation, then you have a Hopf algebra. Now that relation looks a little bit unappetizing, I must admit, but it's nothing too complicated. What it tells you is, take an element, so act with this thing on an element. Okay, so G, think of a G here. Delta on G is going to give you a tensor product of 2 elements. Now, on one of them you do nothing, you keep it the same. On the other one, you act with this element called the antipode. Multiplied, this n means you multiply these 2 now. You do normal multiplication, and what you should get is an identity. So what this tells you essentially is that there's an inverse element that you can take. So this is a mathematical statement of that here you do nothing. So this is the same element twice, more or less. Like if you think of the previous case, it was x times 1 plus 1 times x. On the first one, you take the antipode of x, and then you add it to the one where you have done nothing, because the antipode of 1 is 1, and you get and then you multiply them, and that should give you whatever the identity is, which in this case would be 0. So what you're saying is that there's an inverse element. You don't need to worry about this definition. I'm not going to really use it, but it's just technically what distinguishes a Hopf algebra from what is more generally known as a bi-algebra. Okay, think of it. Another way to think about the existence of the antipode is what guarantees to you that for any representation of your algebra, there's also a dual representation. Okay, which you can then multiply and then get an identity somehow as part of it. So that's another way of thinking about it. But roughly, it's the existence of the inverse element. So one of the last things I want to say about, okay, actually I have a few more, and please stop me if this has already gotten way too abstract. But there's another notion that's very important, which is that okay, we would to do something non-trivial, we would like the product, this m, this was the product, and delta, which is the co-product, to both be non-commutative. Okay, non-commutative for m, non-co-commutative for delta. Because, as I just said earlier, for a Lie algebra, the product is non-commutative, right? 2 matrices that don't commute, but the co-product is commutative. So the usual examples of Lie algebras, one of these 2 structures is commutative, the other one is not. And if both are, then you have an abelian algebra. But now we would like them both to be non-commutative to get something interesting out. And however, we don't want to do this just blindly. We want to do it so that there's an equivalence relation between the co-product and what we would call maybe the opposite co-product, the one where you exchange the 2 copies. And the claim is that you get something interesting if you take the co-product, you exchange copy 1 and copy 2, and of a given element. So you start with an element. This could be Sx, Sy, something simple. You get 2 copies of that. You exchange, and that should be related to the original one, the unexchanged one, by conjugation of the matrix. If this happens, and this R, which of course has to act now on 2 copies, because this lives in 2 copies of the algebra, the co-product, then it's called an R matrix. And if on top of this, okay, so this is what one of the basic requirements, And if it also satisfies this relation, okay, which I'll have a few more things to say about a bit later, then, and here I write it in indices for those who don't like this tensor notation, this sort of algebraic notation, then it's known as a quasi-triangular Hopf algebra. And that's somehow what colloquially we call a quantum group. Okay? So basically all I've done is basically what Fernando was asking earlier. I take on the algebra and I just find a new coproduct which is not co-commutative. If exchanging the coproduct can be done by conjugating with a matrix, and that matrix satisfies this relation, then I have a quantum group, a quasi-triangular Hopf algebra. Okay? That's the idea. Now, the Yang-Baxter equation, of course, is something that is very physical, and indeed many of these ideas came from physics, from the study of integrable systems, the integrable spin change in one dimension, and so on. So what does this relation mean? Maybe just to explain this just a little bit more. When you have R, say R12, it's something that takes, it acts on the module, the representation space, and it exchanges. That's what comes out of that. It's not obvious, it's not on this page, but that's what actually it really does. R exchanges your two copies of your space. So if you have two copies of your Hilbert space, of your single, say, particle Hilbert space, it does exchange. So the way you should think about it is as some kind of operation where R12, so if you start with 3 particles, say 1, 2, 3, and these are the 3 copies of this space, so the particles live in some kind of space, well, one thing that you can do is you can act with R12, exchanging these two, then you can act with R13, right, because this is still 1, and it exchanges, and now if you had drawn this correctly, you could act it once more with R23, and what this relation tells you is that the Yang-Baxter equation is that this should be the same if you did it in a different order. So you still start, so now what you end up here, sorry this is not very clear, but this is 3, 2, and 1, and what you would get here, 1, 2, 3, then you first do 2 and 3, then you do 1, and you get 3, 2, 1. So basically what I've done, what this operator here does, this combination of R's, is take me from a copy of V1 times V2 times V3 to a copy of V3 times V2 times V1. Right? As you can see what happened here. So I've changed 1 to 3 to 3 to 1. Right? And but it turns out that if that equation is satisfied, of course, it doesn't matter in which order we do it. Yes?
Could you tell me what tau12 was doing?
Yeah, so tau12 is the exchange of, so if you have the coproduct, so say delta of x equals x times 1 plus 1 times x, then tau12 on this is what exchanges basically, so you know, it exchanges V1, V2 with V2, V1.
I guess so. I was thinking it looks like R12.
Yeah, but this is just an exchange. I mean, of course, R is something more complicated. I mean, R is a non-trivial matrix. This is just a simple, you just take the symmetrical.
Okay.
So it would maybe correspond to R being just P12. R12, P meaning the permutation.
So a special case of R would be tau.
Yeah, you could think of it. But tau can also act on R. Like I mean, this R. So think of R as some sum of some coefficients ij, ti times tj. These are some matrices, which are the generators. You can act with t12 also on R, and that would exchange these two. So it will leave the C alone, but it will exchange these two. So it's a kind of an operation. R is a matrix which lives in two copies of the algebra. Tau is an operation that you do in the algebra. So it's slightly different the way we talk about it. So anyway, now why do we care about this? If we're physicists, we care because, of course, this, as I'll say a few words in a minute, is the starting point for many discussions of integrability. Right? So when you have integrable systems in physics, they tend to require something like this. And I'll say a few words about why. But from a mathematical perspective, what actually guarantees is something else. Basically, it's the statement of associativity or co-associativity of your algebra. And you can argue also why do we care about co-associativity, why does an algebra need to be associative. I'll come back to what associativity really is about. Well, we care about it because if you define an algebra, if you just take an algebra and define some random coproduct, just put a Q somewhere and you define it, what you'll find is, okay, this defines for you some kind of quadratic relations in your algebra. Now you want to find some cubic relations, so you want to find, well, is I multiply 2 elements times a third, or I multiply 1 element times other 2. Now, does this give consistent relations? Because you can write down relations between these things, and what guarantees that these things are actually consistent? It could turn out that you can write relations which force some of these elements to be 0. Because somehow you can write things that don't make sense unless things are 0. And the Yang-Baxter equation is what really guarantees that this doesn't happen. That you can actually work with multiple copies of your algebra, and everything is well defined. Yes?
By integral persistence that use that structure, are you talking, is that a general statement, or you are talking about, I don't know, something like n equal to 4 with in the Legend plane?
Yeah, that would be an example, of course, that I will care about. But no, this is a very general statement for spin chains. So let me talk about it in the context. So, because n equals 4 integrability comes through the study of spin chains. So anytime I give you some kind of spin chain, and you think of, so where this in practice is relevant, of course it doesn't have to be a spin chain, it could be some kind of classical integrable system as well. What you care about is that if you have, think of these as being 3 magnums on your spin chain. Now, 2 of them interact, and then the third one interacts, and then, now what happens is that the interactions are such that, okay, of course momentum is conserved in any scattering of particles, but what you want more for integrability is that not only the sum of the momenta of these 3 particles is the same, but also every scattering is a 2-particle scattering, which means that actually even the individual momenta that can be permuted, but they don't change. Okay, so it's a very kind of elastic kind of scattering where the momenta, the individual momenta, stay unchanged, and that's one of the somehow signifying features of integrability. So this could be, some particles, in some Sine-Gordon model, or there could be spins on a chain. So you have, some kind of magnons, 1, 2, and maybe somewhere there a third one, and you let them scatter. And if this equation is satisfied, of course, this is not exactly. There's an equation you could write out of an S matrix that is more relevant in that case, but it's related to it. So that's kind of the kind of integrability I'm talking about. I think maybe it appears on this slide, so that's exactly an example. Let's think of a spin chain. You have some spins valued in SQ2, and for instance, and this is the Heisenberg Hamiltonian. We heard a bit about that earlier today, I think, from David. So you see that the Hamiltonian looks roughly like some kind of permutation. I plus 1 is you take 2 elements and permute them, and look at there's some identity which is not very relevant. It's just some overall factor. And the question that you have, your task, is suppose you have the system and there's many of these magnons and many of these. So this is many of these spins, and some of them are pointing down, some are up. Diagonalize this. Give me the energy of this system, right? So add to this Hamiltonian. You see this Hamiltonian acts individually on each 2 of them, because I goes from 1 to L is the length, and it acts as a nearest neighbor interaction. So how do we diagonalize such a system? And the answer was given to us by Beethe. And this is going to be the shortest introduction to integrability ever, but it's not going to be relevant, because I'm not talking about integrability in this talk. But you can write down an R matrix which is related to this Hamiltonian. Actually, it's related by some kind of permutation. And so actually this element I times I actually comes from the permutation one, and this B comes from that one. There's somehow, the relation is somehow like that. But what is important for the R matrix is that there exists a parameter here known as a spectral parameter. And it satisfies a Yang-Baxter equation, which is not the one I wrote before. It's the one including this thing called the spectral parameter. And it also can be used in this algebraic Bethe-Ansatz technique, which of course was developed not by Bethe himself, but it was developed much later by the Russian school, like Fadeev and all that, is that you can define something known as a transfer matrix, which depends on the spectral parameter, from which you can get something. Okay, sorry. The transfer matrix is the trace of this big matrix to the right, which commutes with itself for different values of the spectral parameter. And if you can achieve that, and the R matrix is instrumental in being able to do this, so if you have an R matrix, you can also already see it because this thing looks like the Yang-Baxter equation, which is up there, or maybe it's the previous page. If you take the Yang-Baxter equation, you trace over the third copy of your algebra, then basically you get this. So if you have the Yang-Baxter equation with spectral parameter, and you kind of trace over one of the spaces, then you already get T, where T now you just take a trace in the remaining. So when I say trace one, it's a trace in the first copy of the space, and so on, and then you get the small t. And now the fact that these commute for different values of the spectral parameter is what leads to an infinite number of conserved charges, and that leads you to integrability. So basically, you have an infinite number of commuting quantities in your theory. So what I'm taking out of this is, of course, that integrability requires not only that Yang-Baxter equation I wrote, but that Yang-Baxter with some extra parameter here, this complex parameter U. Okay, so just an example of how these things look. For SU2, for instance, if I take two copies of my algebra, that will be spanned by, so suppose now I want to act on two copies of my fundamental representation, so that will be given by x and y. So this is going to be a four-dimensional space that I'm acting on. And so think of this as being xx, xy, yx, yy. Okay, think of this as these two spins that I was talking about. Call up spin x, down spin y, and you have xx, xy, and so on. It turns out, okay, this is the Hamiltonian of Heisenberg in this basis. Okay, now acting on only two spins, and the R matrix is the R matrix looks like this with a spectral parameter. And since I'm not necessarily interested in integrability at this point, I'll come back to the very end to integrability. I'll work in what is known as the quantum group limit, where you take this U to infinity. And this R matrix for SU2 is going to be very simple. What happens here if you take U to infinity is that you just get 1, 1, 1, 1, because there's a U here, and you get just this. What does it mean to have this R matrix? Remember, the R matrix is what exchanges my two copies of the algebra. So if the R matrix is just identity times identity, it means that exchanging the two copies is the same thing. And if you remember that there was a formula about the coproduct, it means that the coproduct is symmetric, and it means that we're back to the Lie algebra set. So the Heisenberg spin chain has SU2 symmetry. That's what this slide is kind of telling you in a very roundabout way. But it was, of course, known from the beginning. If you go to SU3, just to set up some notation for later, now my copy of this is the representation space, it's spanned by 9 elements, xx, xy, xz, and so on. And so basically, I can write, this is the permutation matrix. Okay, this is just an example of a matrix that works in the spaces. Okay, so this permutes two copies of my two copies of the algebra, 1 and 2. This just as an example, but P is going to be the same thing. R is still going to be something related to identity plus this. But the important thing is that, again, if I take this U to infinity limit, my R matrix is still the 9 by 9 matrix, which is identity times identity. Okay, is it clear why this is 9 by 9? I mean, the identity is going to be a 3 by 3 identity, because that's what acts naturally. I'm talking about SQ3 in the fundamental representation, and one of these matrices is going to be just identity that will form my basis. And again, we get the co-commutative coproduct, and we have an SU3 algebra. So far, so good. Now, let's go back. Let's think a little bit more generally about how we move more out of this Lie algebra setting. And one of the ways that Drinfeld showed us how to do is, given an initial algebra, we can twist it to produce a quasi-Hopf algebra in general. I haven't defined quasi-Hopf, it'll come in the next slide. But what you do is, you have another matrix, F, which lives in two copies of the algebra. And you take a coproduct, you conjugate it with this matrix, but and then you get a new coproduct, delta F, which is supposed to be now your non-co-commutative coproduct. And your new R matrix is given by this. So you start with an original R matrix, which might be identity times identity. You twist, and you get this. Okay? And now I emphasize here that this is not conjugation. Because here I've exchanged my copies 1 and 2 of my algebra. Here I haven't. This is still 1, 2. When I don't write anything, it's 1, 2. So what that means is that this is not just taking some structure and just conjugating left and right. This is actually giving you something which is quite inequivalent. And to get something known as a Hopf algebra, we need to satisfy a condition here. If it does not, and this guarantees the Yang-Baxter equation, if it doesn't get satisfied, you get something known as a quasi-Hopf algebra. So these are non-coassociative algebras because the Yang-Baxter equation is not satisfied, and the non-coassociativity is controlled by this thing known as the co-associator, which is an element which now lives in 3 copies of the algebra. Why does it need to live in 3 copies? Because this is how we in these kind of notation, we talk about you take an element here, and this kind of these diagrams I drew earlier, these diamonds. You take an element, you act with the coproduct, and now you say you act with the coproduct on the right. You want this element to be related to the cubic element that you get by acting on the left, and the way they're related is through the action of this co-associator file. So basically, we have a setting where there is non-associativity in the structure of the co-structure of algebra, but it's completely under control. If you know what phi is, you can always switch the parentheses. That's what this is telling you. You can switch the parentheses from the left to the right whenever you need to do that. And we'll see an example of it. And the co-associator is defined through this through the twist in the same the same twist that defines for you the R matrix, which is here. It also defines for you the co-associator. Now, what is this? And now if you have the co-associator, you can write down what is known as the quasi-Hopf version of the Yang-Baxter equation. And now let's compare this equation here to what I had written there, just to see why this is kind of why it looks funny like that. Well, the problem now is if you're working in a non-co-associative setting, you cannot be kind of cavalier about expressions like these. Whenever you have an expression like these, and you need to tell me where is the parenthesis. Okay? Otherwise, this is not a sensible expression. If you don't put the parentheses in the right order, you get something which is nonsensical. So, for instance, if you want to redo this calculation here and act with R12, let's say you start with, and I'll use some kind of graphical notation where I put 1 and 2 close by, and then 3 farther away. Having them close by means that the parentheses is around 1 and 2. So now, of course, here, and there is also a slight, okay, I'm not going to draw it very nicely on the blackboard, but you can think of R, for those of you who've seen braided algebras, you can think of R as a braiding, meaning that it's kind of nice to think of R as one of the lines above and the other one below, because it allows you to actually prove many identities like that. So if you think of R like this is the action of R12, okay? But now, what I would like to do is I would like to act through the R13. Now, 1 is here, right? My particle 1 has moved here, particle 3 is still here. Now, how can I do it? Because at this point, my vector space, so here I start with the V1 times V2 times V3. Here I got V2 times V1 times V3. But now V1 cannot really interact with V3 unless the parenthesis gets moved. So to do that, I need to be in V2 times V1 times V3. And the appropriate element in my structure that does it is the co-associator. So basically I need to act, and let me draw it like this. So I'll draw the action of the co-associator as a horizontal line. And this is phi, and now if you think of how the elements are arranged, this is 2, this is 1, this is 3, so this is actually 2, 1, 3. Okay, this is if you think of how the copies are arranged at this point. Now I'm allowed to act with R. Let's see, this is 1, 3. Now I want to act with R to 3. Okay? How can I act with R to 3 again? My problem is that now, after this action, I have now V2 times V3 times V1. So I have to use a co-associator. This time it's a co-associator that takes a right parenthesis to a left parenthesis, so it's going to be the inverse of the co-associator. So this is now going to act like this. And this is going to be, okay, this was the same, that happened here. And so this now, if you count again, this is 2, this is 3, this is 1. So this is 5 minus 1, 2, 3. Now you can act with R 2, 3. And now if you want to compare, for instance, V1 to V1, V2 times V3 with, say, this, then you need to use one more co-associator, like this. So, and this would be 5, this is 3, this is 2, and this is 1. Okay, to get to the point where you have 3, 2, 1, and now you see there are 2, 1 are close together, so that's what the parentheses are. So that's a rough idea. Now you have to do it on the other side. And the beauty is that if everything works the way they're defined here, the definition of the co-associator is given, and that is there. Of course, this is maybe not the easiest thing to get to grips with. I'll explain a little bit later how. But then what you get is that you should still get an equality. And that is known as the quasi-Hopf Yang-Baxter equation. Okay. So this slide shows what I kind of half of that I already showed on the blackboard. That now this is what the calculation did on the blackboard. Now this would be the other side of the identity where first you need to change the parentheses here, then you act with R, and you continue like that. And this hopefully gives you a feeling of the structure of this quasi-Hopf Yang-Baxter equation. All right, that's more or less all I had to say about algebra. So now I'm going to physics. Okay, in the remaining, I guess, 20 minutes or so, right? So what I'm going to do now is, after we gave this kind of maybe lightning sort of overview of quantum groups and quasi-Hopf, and okay, it probably doesn't make much sense, and you might be wondering why am I spending all this time on it. Well, let's discuss the exactly marginal deformations of n equals 4 super elements. Now, n equals 4, as already has been discussed in this school, is a very special theory. You can think of it as the unique 4-dimensional gauge theory with the maximum amount of supersymmetry, and for many, I mean, it has so many beautiful and interesting properties, like perturbative finiteness, for instance. So it's a theory where if you calculate, if you try to calculate Feynman diagrams of 1 loop, 2 loops of fundamental fields, you will never find any divergences, any UV divergences. And this is actually, since this is the Mandelstam school, of course, this is something where Mandelstam played a major role. He provided the first all-orders proof of this statement, that there are no UV divergences, using light cone superspace. So this, of course, had been done before by various people, also Crisaru, Rocek, and Siegel, and some other groups have done it up to 3 loops, some of them using superspace, some of them not. But this light cone superspace approach was definitely one of the most fundamental ones. So let me go back to the other slide. Okay, but beyond perturbative finiteness, of course, it's also a theory which is non-perturbatively finite, as we believe. I guess this probably became clear maybe in the late 80s, early 90s with the work of Seiberg on holomorphicity and all that, or maybe some of you know the story a bit better. But definitely it's believed to be non-perturbatively finite. It's believed to, I mean, it is definitely part of the ATS-CFT correspondence. It has planar integrability, as we heard about a bit earlier today. Planar amplitudes have very interesting structures and properties, also related to integrability. And you can ask the question, okay, are there any, I mean, beyond this, which is of course a very beautiful theory, are there any other ones that share at least some of these features? And, well, just again, for the students, let me just say what this theory is made of. David already kind of discussed this, but there's a gauge field, there are 4 spinors, and there are 6 scalars, which I choose to write as an anti-symmetric 2 tensor with A goes from 1 to 4. It doesn't really matter here. They're matrices. They live in the adjoint of a gauge group, which I take to be SUN. And in n=1 superspace, you can describe them in terms of superfields. So you can put them all in some structure phi, which has the superspace coordinate. And the relevant part is the superpotential. Okay, what I will care about. There's a kinetic term, but somehow the interactions that I am interested in are in the superpotential, which is given by this. So you can write it either as phi 1 times the computator of phi 2, phi 3, or this can be rewritten up to some factor as a totally antisymmetric combination. So the potential gauge related is given by derivatives of the superpotential. That doesn't matter too much. I'll focus on the superpotential. Now, Minahan and Zarembo, as you also heard, argue that this theory is integrable. At least their work was in the scalar sector. And the way that works is you take the planar limit, and they found out that the observables of the theory are the gauge invariant operators. And what they found was that you can, if you write your operators like this, so this is an operator in n=4 PMLs, and you can write it in terms of the scalar fields of the theory. So it's some combination of the scalar fields, where x and y are some plus or minus I of these phi 1, phi 2, phi 3. Actually x, y, and z are exactly phi 1, phi 2, phi 3. And you want to diagonalize the dilatation operator of the theory, since this is a conformal theory, as I mentioned a bit earlier, because it's exactly finite to all orders. That's difficult, but the dilatation operator, that was the main achievement, works exactly like a Heisenberg Hamiltonian. So you can apply the Bethe techniques and integrability to solve the n=4 spectral problem. Okay. So that was just to emphasize somehow how important integrability has been in all of this notion. Now what I'm going to do is look for theories as close as possible to n=4, which preserve conformal invariance. So these are going to be marginal deformations. And also I wanted to preserve n=1 supersymmetry, and that actually restricts me to theories that I can get by changing my superpotential. Okay? So I'm not going to touch the kinetic terms, I'm not going to mix the kinetic term with the superpotential. So the most general classically marginal deformation can be written like this. It has to be cubic, because I want something which is quartic in my potential, and only if you have a cubic superpotential can you get a quartic potential. But since epsilon IJK has already been used, that's the original superpotential, well, my only, up to some relabeling of fields, HIJK has to be symmetric. Okay. Now, how many are exactly marginal? That was, again, perturbatively, there were approaches in the early 80s, but the non-perturbative proof was given by Leigh-Strassler, and they ended up in some choice. This is kind of basis dependent. I mean, you can always do unitary transformations of fields and make things look a bit different. But in the canonical way of writing it is like this. So this gives us, if you take Q to be 1 and H to be 0, this new H parameter, these are complex numbers. Q is a complex number which appears like this. H is a complex number. Kappa is a complex number. If you take this limit, you recover just, this goes away, and you recover just n=4. F is a function of the gauge coupling kappa, H, and Q, which if this function is satisfied, then this theory is superconformal. So we do not know this function. All the Leigh-Strassler argument tells us is that there is a function, because it was basically doing kind of counting of how many, because there is some kind of Z3 symmetry which allows you to equate some anomalous dimensions of fields, and how can you put all of them to 0 at the same time? And that's how they came up with. So this satisfies, as I'm going to show in the next slide, a very important property, which is a permutation symmetry of the scalar field. Otherwise, you would not be able to make this Leigh-Strassler argument. And okay, just to show that this can be made concrete, this is the finiteness condition to one loop. There are results known to slightly higher loops, but it's something which, of course, we would not know. We would really like to know this function at all loops if possible. That guarantees exact conformal invariance, but it's not currently known. An interesting case, which will come up often, is when Q, this parameter that appears here in this Q commutator, is just a phase, e to the I beta. I'm not sure how visible it is down here. But that is known as the real beta deformation.
Sorry, but so you introduce two parameters, Q and H?
And kappa.
Kappa, all complex,
yeah.
And then you will only have one constraint.
Well, and the conjugate. of this one.
Right. One complex constraint.
Yeah, one complex constraint. So I think the logic is that n equals 4 is of course not one theory, it's a line of theories, right? Labeled by tau, and you should be able at any point to move away in the h and q direction.
Yes.
Right? So you expect a two complex dimensional manifold, and kappa is whatever it needs to be for the equation to be satisfied. Okay, so you can think of h and
Oh, I
q.
see. So you think of that as an equation for kappa.
Yeah, you can think of it as an equation of kappa. So basically, we know it's going to be a two complex dimensional manifold. You can ask questions about what is its geometry, or is it Kähler? I think it's going to be Kähler.
Is the theory S-dual? Do you preserve S-duality?
Well, S-duality acts on tau. I'm not sure. I think the statement is yes. I mean, if you know how to act specifically on H and Q, yes, then you should have S-duality in the full story. That's actually exactly what Leigh and Mandelstam did. They understood how this beta parameter should change under S-duality. No, the duality was for TST, but then they actually did S-duality to get the imaginary beta. Of course, yeah, T-duality was crucial, but then eventually they understood that if you do type 2B S-duality on the real beta solution, you should be able to go from real beta to imaginary beta. Okay, so that's what at least they claimed was that's how they got the full. Because Leigh and Mandelstam actually got the full background, not only the real beta, but the general complex beta, and they used S-duality, type 2B S-duality. But yeah, so well, I'm not sure what the results are known for H, but if you only stick to Q, there is a bit known about this. Okay, so anyway, how can we compare these theories? They're both conformally invariant. In terms of ATS-CFT, Leigh and Mandelstam in 2005, they found the complex beta, as I just mentioned, using combination of TST and S-duality. Planar integrability, of course, n equals 4 is believed to be integrable. For Leigh-Strassler, so these general theories, we are more or less stuck with real beta. And originally people had hopes that you also for the general Leigh-Strassler theory, you'd get an integrable spin chain, and it was work of David together with Sergei Cherkis, I think mainly, which put a kind of damper on these expectations, and they showed that the S matrix that you get for the particular spin chains that you would get for the general theory does not satisfy Yang-Baxter, and so basically that kind of killed that idea from the spin chain side. Also from the gravity side, there's work. I was also involved in some work that used this method of analytical integrability, originally developed by Palab, who was here at some point, and Johan Pandozayas, which basically you study classical strings on the dual background, and if you study classical strings on the real beta Leigh and Mandelstam background, you find that everything works nice, and you get what looks like integrable solutions. But the moment you turn on imaginary beta, you lose integrability. And you can prove that analytically.
So how many supersymmetries do you preserve?
These are all n equals 1. These are all n equals 1 background. Of course, we cannot do this test for H because the background is not known. So, but we did it for real imaginary beta. So what's so special about real beta that kind of leads to it being integrable and everything else not? Okay, I don't know exactly. But let's focus a bit on the symmetry. Okay, the symmetry, you have the superconformal symmetry. In that, you have this SO6 that was mentioned earlier today. And in n equals 1 superspace, the part of this SO6 that's manifest is actually an SU3 times U1. There's a U1 acting within phi, and there's an SU3 which rotates these phi's among themselves. So think of these phi1, phi2, phi3 as a column, and you can have an SU3 which rotates them. And the reason that this is invariant under SU3, and again this is for the students, is suppose I take phi to u phi, so phi j to u phi j, and phi k to u phi k, then what happens is that I extract from here 3 u's. Now they get hit by this epsilon symbol, and what happens to epsilon times u? Well, that gives me a determinant times an epsilon again. The determinant of SU3 is 1. So since so this matrix here, U, that I transform my phi, has to be an SU3 matrix, otherwise it would not be. I mean, there are other reasons, but I mean, this is one way of seeing why this is invariant. So if you take phi to u phi, with u being an SU3 matrix, this is invariant. Okay. What about Leigh-Strassler? What are the symmetries of Leigh-Strassler? Well, if you look at this, in general, there's not much. You still have the U1, which rotates phis within themselves. I mean, that acts on the superspace coordinate theta. But the U1R, but you totally break the SU3. Well, not totally. What remains is some discrete symmetries, like the symmetry phi1, phi2, going to phi2, phi3. That is preserved, and that was actually crucial for the argument of Leigh and Strassler to work. And Aharoni and friends, they looked at this and they found actually some non-abelian discrete group called delta 27 that is the actual symmetry. If you have real beta, then this part is not there, and you actually enhance the symmetry to some U1 cubed, and that's actually what allowed Leon and Maldacena to proceed, because they could do T-duality along one of the U1s, shift with a real parameter along one of the other U1s, and then T-dualize back without touching the third U1, and that led to an n equals 1 background, because if you touch all three of these U1s, then you're going to break supersymmetry. You need at least one to be ideal. Is this everything? Okay, to answer this question, I'm going to go now to R matrices again. So back a little bit to the discussion we had a bit earlier. And I'm gonna, so Royban showed how you can take the Lagrangian of the theory, write it out explicitly, not in superspace, just write out the scalar terms, and from that you can extract the one loop spin chain Hamiltonian just directly without really doing any work. And that's how this Hamiltonian looks. So this is the Hamiltonian of the spin chain that, this is not exactly the same form that David and Jerkis analyzed, but it's just a rewriting of that. But you can, the R matrix is defined through some permutation, which you can see here, ij becomes ji, and you get, this is the actual R matrix of the theory. So this is something that you want to now take and put in the Yang-Baxter equation and check whether it's satisfied or not. All right. And half 10 minutes or less? Yeah. Okay, so in n equals 4, you can see that, well, if you look here at the R matrix, I'm not going to go through the reasons for this switch from Hamiltonian to R matrix, but it's something that's well understood. You find that QQ bar is 1, H is 0, and so if you work out everything, this is just identity times identity. It's a 9 by 9 identity matrix, which is what I'm saying here. The main result of this work I'm presenting is how do you understand the most general R matrix that was there in the previous slide. Well, it can be written in terms of a Drinfeld twist. Okay, so this now you have to go and remember the first part of the talk when I define the Drinfeld twist. But I claim that given an initial R matrix, you can twist it to get another R matrix. And this is not a simple conjugation, it's something more complicated because there's a 2-1 here and a 1-2 here. So these are not equivalent matrices in any way. Well, they're equivalent in this way, but not in the usual vector analysis way. And you can show that this R matrix, of course, which gives you what was in the previous slide, does not satisfy the Yang-Baxter. So when it does, it's known integrable deformation, but generally it doesn't. As a simple case, this is the beta deformation. Q is a phase. The R matrix is diagonal. And as you might imagine, this satisfies the Yang-Baxter equation. It's quite a very simple matrix. And everything is nice and quasi-triangular and all that. So, and you can get the twist that gives you that, and you can express it very simply as an exponential of Cartan elements of SU3. So these are the two Cartans of SU3. Well, in some choice of them, you could have written this in terms of the 8th Kelman matrix if you wanted, and that's what you do. So it's a very simple abelian twist, because these are abelian matrices. And when I write H1 with H2, what I mean is, so when I write two matrices like that, what I mean is H1 times H2 minus H2, tensor product H1. So these are all 9 by 9 matrices, because these are 3 by 3 because we're in SQ3, and they live in the double product, so they're 9 by 9. In the tensor product, so they're 9 by 9. Good, so in general, and that was one of the big technical things that we did, we needed to find a twist, FQH, which gives you that R matrix. Okay, and it turns out we can find it. A and F, I'll show them on the next slide. They're complicated functions of your original Q's and Q bars. But you can take the R matrix of n equals 4, which is just identity, 9 by 9 identity, and you can get that R matrix by applying this twist. And this twist, okay, if you want to be more careful about it, so it looks somehow like this as a 9 by 9 matrix, where these expressions are given by that. Okay, so it's an explicitly known twist, which satisfies all the usual properties. So there's an identity here, so F21 times F12 minus 1 gives you the R matrix, and it satisfies this known as a triangular condition. Good, so now, of course, what we want to do is, I'm claiming this is a quasi-Hopf algebra. Okay, that's where this is going. How do you find that this is a quasi-Hopf algebra? Well, you need to find the co-associator, and then you need to check the quasi-Hopf Baxter equation to make sure that this is really a quasi-Hopf algebra. And we don't know how to act. I mean, how do you make sense of an expression like this? Okay, that's also something that technically took us a bit of time to understand. But because the problem is that you only know how to act with the coproduct on algebra elements. So like this, for instance, but you don't really know how to act on the group element because F lives in the group and not in the algebra. It's an exponential of algebra. So, but there is a way to do this. I mean, if you can manage to write F as exponential of an algebra element, where F is kind of written like this, where lambdas are Gelman matrices, 3 by 3 Gelman, then you are able to exponentiate the coproduct, because there's a compatibility between product and coproduct. And then what you need to do is exponentiate this matrix, where now this is going to be not 9 by 9 anymore, but 27 by 27. Okay, it's going to be a 27 by 27 matrix. So you now reach computational hurdles in doing this, but okay, it can be, well, at least it can be done. In simple cases, it's very easy. Otherwise, you might have to resort to numerics. But explicitly, F, the 9 by 9 F, if you write it like this, and this is work of where Hector has played a major role in getting these to work, you can write in terms of 3 or 4 classical twists, and with some parameters which are given here, so you can see that things are complicated. These are complicated functions of h's and h bars, but knowing this, you can calculate this, and eventually you can calculate the co-associator. Okay, so to conclude, more or less, we've constructed this, and we can check this quasi-Hopf Baxter equations. Sometimes you can check it more or less kind of by following the definition, but in simple cases you can even put it mathematically and just check that this is satisfied. And the claim is we have something known as a triangular quasi-Hopf algebra. And the statement I'm making is that this is the actual global internal symmetry of the Leigh-Strassler theory. Okay? So it's something that, so the SQ3 that was there for n equals 4 is not broken, it's not gone, it just got deformed to a quantum algebra. Now, you might immediately complain, okay, I mean, the main complaint that one has if you move beyond Lie algebra symmetries for a real theory, a real QFT, is what about statistics? What about Bose-Fermi? Because Lie groups, and actually the fact that the co-product has a natural action of the symmetry group is what gives us Bose-Fermi statistics. The fact that you can have symmetric, anti-symmetric. Fortunately, there's work of Fiore and Schupp, which shows that for any quantum group symmetry that you can get from a twist from a Lie algebraic symmetry, there's no problem with statistics. You have to generalize some notions, but your statistics works exactly the same as any normal internal symmetry. So that's fine. And okay, I think I have maybe a couple of minutes, right? So let me quickly go to the last part, which is how do you make this useful? Well, one way to use the symmetry is to define a star product. I'm not going to go through the details because of lack of time, but basically there is a way to use this twist to define a star product. Now, I'm not caring more about the algebra itself, what I call the quasi-Hopf algebra. I'm looking at the representation space, what I call the module. So basically these things. I want to define an appropriate star product on my elements, which are going to be basically the scalar fields of n equals 4. Because that's what I'm thinking of here. These things are, like a basis for this is phi1, phi2, and phi3, my 3 scalar fields, which are in the fundamental representation of SQ3. Now they're going to be in the fundamental representation of my quasi-Hopf algebra. And so this is kind of explaining how it's done. The final answer is this. And so you take the twist, think of these as some coordinates, I goes from 1 to 3, and you can twist like that. And you can also define the inverse of that, where you put an f instead of f minus 1 here. Basically, you can switch around. You can take an expression without a star product, and you can add one, and or you can go the other way. And what it does, what this inverse star product does, is you take an expression which makes sense in n equals 4. z1, z2 minus z2, z1. That's some expression. And you put a star product, and what comes out for you is an expression which makes sense in the Leigh-Strassler field. And now, for this, we're actually very inspired by early work of David and Vishnu and Rob Lee, which showed that there is a quantum plane structure of in the f-term relations of the theory. These are, if you put this to 0, this is precisely, and forget about the star, that's precisely the f-term relations of n equals 4. So what I'm claiming is that f-term relations of Leigh-Strassler can be gotten just by putting a star in the f-term relations of n equals 4. For any QH, integrable doesn't matter, we've shown this in full generality. Okay, so we have found a star product which takes any expression n equals 4. Well, okay, maybe that's a strong claim. So far, any expression we've tried, we get something which is sensible in Leigh-Strassler. Now, to do cubic, you have to be careful because this is not associative. So you have to kind of be a little bit careful with what you're doing. These are the definitions. This is what comes out of them. That if you take parentheses in two different ways, you don't get the same answer. However, if you sum over cyclic ordering, so you sum these three elements, what you can see is cyclic 1, 2, 3, 3, 1, and so on. Actually, now you're allowed to move the parentheses with no co-associator. This is a small miracle, but okay, it has a very good explanation in the end. So the fact that this product, this particular cyclic product is associative, even though the individual ones are not. Of course, here it doesn't have to be 1, 2, 3. I could put 1, 2, 2. Anything that I put would not be associative, but this specific combination is. And the final main thing I want to show is that if you now take this potential of n equals 4, expand it out, so basically you can put the potential of n equals 4 is 1, 2, 3, minus 1, 3, 2. But you can write it in a more symmetric way, by dividing by 3 and writing these combinations here, so like some kind of symmetrized trace prescription. Now, put a star product. What you get out, if you now do the trace back, okay, so this is the formula that is the main formula of this work. You can take the small potential of n equals 4, put a star product, you get the small potential of the Leigh-Strassler, okay, on the node. Up to something which is probably related to kappa, that was there earlier. So basically what I'm claiming is that the Leigh-Strassler theories are not really different from n equals 4. They are related by this Drinfeld twist, which can be very precise in terms of a star product, and there is a way to show that there is a quasi-Hopf symmetry in this theory. So you can take the star product, you can write it like this, you can transform them using some matrices, and you can find that if those matrices satisfy the requirements of the co-products and all that, then you get that it's invariant. Okay, so that's the statement. You have to work much harder to also get some mixed relations because you need to put the star product also in the kinetic terms. It turns out that if you do it correctly, these are invariant. So this is really a superpotential deformation and not a more general deformation. You can think of more general ones, we haven't really. Okay, to summarize the talk, what I've uncovered is a quasi-Hopf algebra structure, which just tells you that maybe we should start thinking of this quasi-Hopf symmetry as a real global symmetry of a real physical quantum field theory, well, real in the sense of n equals 1 supersymmetry, and conformal and all that. And even though we got it from the one-loop spin chain picture, actually it seems to be an exact symmetry of the classical Lagrangian of the theory. Because whenever I say anything about that, n did not play a role, they're not of the gauge group, I was not in the planar limit. I'm just taking the tree-level Lagrangian and I'm showing that it has a symmetry, which is a quantum group symmetry. So it generalizes previously known star products for some integrable cases that we had looked at earlier. And what we did in previous work with Hector is we showed how, in the integrable cases, but not beta, there are some other integrable cases which are slightly more complicated, we showed that you can apply the star product on the supergravity side as well. Because as the general statement, of course, is in ADCFT that if you have a global symmetry in the boundary, you somehow expect that to get manifested somehow in the bulk as some kind of isometry. We're not claiming we have a quantum group isometries of anything, but what we did was we used the framework of generalized geometry, where you describe everything in terms of differential forms, called pure spinors, and we put some star products there, and by the time you follow the star product and you expand it out into something without star products, what you get out is the exact background. Well, it was a new background, but kind of related to Mandelstam with some diffeomorphism. So it was not exactly a totally new background. But it somehow, the hope is there that maybe by using the star product, eventually, so if you fully understand the quasi-Hopf structure, you might be able to construct more general dual backgrounds. So for instance, the H background, which is still unknown, the pure H background. And you can think of whether similar structures might arise in other theories. Are there relations to other kinds of solution generating techniques that have appeared recently in the literature, like the classical Yang-Baxter equation and so on? Like, can you use this to actually generate some new solutions in supergravity, knowing the actual symmetry of the gauge theory? Integrability, of course, integrability was shown not to be there. To make sure why it's broken and why it's not there, if it's not there, one would have to take everything I've said and include the specular parameter back in the story. Because everything I've talked about is in the quantum group limit. Specular parameter has been sent to infinity. If you can put it back in the story and write the quasi-Hopf Yang-Baxter equation with a specular parameter, then maybe there's some hidden notion of integrability there. Most likely you won't be able to, and that will correspond to what results we'll have already found. Okay, so the final question is perhaps, is there some underlying, we found the symmetry, and of course we know that in 2 dimensions there's very strong relations between CFTs and quantum groups. Is there some equivalent kind of relation here between this new kind of quantum symmetry and the fact that these theories are particularly defined? Or it's just a fluke? Okay, we don't know. Okay, thanks for your attention.
Any questions?
So you were able to rederive the Mandelstam backgrounds by just looking at the quasi-Hopf structure, and then from that.
Okay, we were looking at the integrable cases, so that was just a Hopf structure. It was not quasi-Hopf.
Oh, okay.
Okay, and all you have to do to get that is think of there are these things known as pure spinors in generalized geometry, but there are things like this: dz1 with dz2, with dz3, where these are, if you think of the 10-dimensional setup, you have some d3 branes. And there's a transverse C3, right? So basically these are the coordinates of that C3. So we're looking at that space and just added a star here, which was derived from the star product we had. And there's also another one which looks like e to the I sum of the Kähler form. dz wedge dz bar, something like this. So you put a star here as well, for which you need to know the mixed star products. You expand these out, so because we know what the star means. It means multiply with appropriate matrices, and you get some big expression here. And what you get is, instead of C, you get a C3 tilde, which is not a quantum group. I mean, this is just a normal smooth manifold, but deformed. So it's basically a deformed C3. And this deformed C3 admits an expression as a cone over a deformed S5. And that deformed S5 is exactly Mandelstam. Okay. So basically we're doing Mandelstam without using TST. We never actually really use TST anywhere here. Of course, it's kind of, in a way, it's probably equivalent.
Where's the B field?
You can get the B field because this is generalized geometry. So you have the metric is actually a 12-dimensional metric. So these give rise to a 12-dimensional metric, which looks like G minus 1B, G, D minus 1, G minus 1. I mean, there is some expression you might have seen. So basically what we get from this is the full generalized metric. And from that you can read off the B field. And you can read off the dilaton as well from the determinant of this metric. So basically everything is, so if you look at the generalized geometry people, in their papers, they write these expressions all the time. Right. So that's what we do. That's why we like the generalized geometry, because it gives you the B field on the node. And the nice thing about this method is it's a 2-step thing, because this is actually an n equals it's kind of analytical. It's an SNS background that you get by doing this, because you're only deforming the C3. Now you want to put D3 branes, and you want to take the new horizontal limit. And of course, then you're going to have Ramond fields as well, because Mandelstam also has Ramond. So what we actually got was what they call the NSNS precursor of the Mandelstam. So there's a geometry, which is Minkowski 4 times some deformed C3, where if you put D3 branes and you make that whole thing consistent, like you solve the supergravity equations, you're going to find also the Ramond fields of Mandelstam. Okay. So we were not doing it, we did not get them directly, we did this two-step thing. Unfortunately, if you want to do this for the non-integrable cases, probably you have to sprinkle this with some phi's and phi minus 1s, I mean, to make this sensible, and we don't really yet know how to do that. Okay, so this was a very simple case where it was associative, the co-associator was 1, and you could just very simply do it. Well, simply is a strong word, but I mean, we had, it was not too complicated, but we don't really have very good ideas yet. Phi minus. How to do it for the general case.
So do you know the spectrum of protected operators in this theory?
I believe you should. I mean, that's one of the things, of course, that one should be able to get from these kind of considerations. You should be able to get a protected. Obviously, these are n equals 1 theory, so I'm not claiming that they're exactly the same as n equals 4. Right. Even for the beta deformation, it's known that there are some BPS operators which are not there in n equals 4, right? Because they're too trivial. Like if you take the operator xy or something like that.
Trace of xy now may not be 0 anymore. Trace xy minus trace yx or something.
Yeah, something like this, yeah. So there are some operators that people like, I mean, some people in Berlin have looked at in some detail, of short operators, which somehow are new for the beta deformed theory compared to n equals 4. So there's no claim that everything is the same. And of course, I'm not talking about quantum theory at all here, right? I'm only talking about the classical Lagrangian. So
sure, but when you say that the theory for a specific point is conformal, you are talking about the quantum theory, no?
Yeah, in that sense, yes. I mean, if you can do that, but I'm not sure any of this will help in, for instance, getting that conformal function, the conformal manifold, because you still have to do a loop calculation order by order and then fix kappa order by order. I don't have a way of getting. Well, there is a kappa that came out of this. Okay, so this you could think of kappa because that's what arises in front of the super potential. I would be very surprised if this kappa would be the full answer, because obviously it does not depend on the gauge coupling. I mean, so you have to still do the loop calculations.
Yeah, but sorry, but no, of course this may not be the full answer, but the statement I guess is that there is a critical point at which you have a relation between kappa, h, g, etc. Yeah. And for at the critical point, the theory is conformal.
Yeah.
Also quantum mechanically.
Yeah, if you knew that function, that if you knew what kappa is order by order in loop order, yeah, you would be able to be there. But if there is the hope would be that there is a nice non-perturbative function that gives you the conformal manifold exactly. And people have tried, using the fact that it's scalar and all that, maybe to find some appropriate coordinate system on this, but I don't think there is much.
Right. Any other questions? If not, let's thank Kostas again.